We will be discussing the properties on determinants. So the first property is the value of the determinant remains unchanged if its rows and columns are interchanged. That is, if we change the row elements into columns and column elements into rows, there is no change in the value of the determinant. The above property can also be written as if A is a square matrix, then the determinant value of the matrix is equal to determinant value of its transpose. To understand this property, we will consider one example related to the above property. So consider delta is equal to 2 minus 3, 5, 6, 0, 4, 1, 5, minus 7. So solution. So first we will expand the given determinant using the first row. So write down the elements of the first row, that is 2 into the 2 cross 2 determinant 0, 4, 5, minus 7. Next, second element minus 3 with a multiplied with a negative sign and write down the 2 cross 2 determinant obtained, that is 6, 4, 1, minus 7. Next, the last element 5 into the determinant 6, 0, 1, 5. On simplifying, we get 2 into 0 minus 20 plus 3 into minus 42 minus 4 plus 5 into 30 minus 0. On further simplifying, we get minus 40 minus 138 plus 150, which equals minus 128. So next we will interchange the rows into columns. So delta dash will be 2 minus 3, 5, 6, 0, 4, 1, 5, minus 7. We will expand it along the first column. So 2 into the determinant 0, 5, 4, minus 7. Next, minus of minus 3 into 6, 1, 4, minus 7 plus 5 into the determinant 6, 1, 0, 5. Again, on simplifying, we get 2 into 0 minus 20 plus 3 into minus 42 minus 4 plus 5 into 30 minus 0. So on simplifying it further, we are getting minus 28. So here we can see that the value of delta and delta dash are both same and are equal to minus 28. So according to the first property, the determinant value of A is equal to determinant value of transpose of A. Hence property 1 is verified. Next, property number 2. If any two rows of a determinant are interchanged, then sign of the determinant changes. So here, if we are changing R1 into R2 or R2 into R3, so when we are applying the interchanging operation one time, the value of the determinant gets multiplied by a negative sign. To understand this, we will consider an example. Let delta is equal to 2 minus 3, 5, 6, 0, 4, 1, 5, minus 7. So we will expand the determinant along the first row. So write down the element of the first row, that is first element of R1 is 2 into 0, 4, 5, minus 7. Next, minus of minus 3 into 6, 4, 1, minus 7 and plus 5 into 6, 0, 1, 5. Again, on simplifying, we get 0 minus 20 plus 3 into minus 42 minus 4 plus 5 into 30 minus 0. On simplifying, we are getting minus 40 minus 138 plus 150, which is equal to minus 28. Now we will interchange the elements of R2 with R3. So the given determinant will be 2 minus 3 5, 1 5 minus 7, 6 0 4. Again we will expand it along the first row. So 2 into 5 minus 7 0 4 minus 3 into 1 minus 7 6 4 plus 5 into 1 5 6 0. So we get 2 into 20 minus 0 plus 3 into 4 plus 42 plus 5 into 0 minus 30. On further simplifying, we get 40 plus 138 minus 150. So the value of delta 1 is equal to 28. So when we compare the value of delta and delta 1, we can see that numerically they are same, but they have opposite sign. So when we apply the interchanging property, the value of the determinant only changes in the sign. So delta dash is equal to minus delta. Next, property number 3. If any two rows or columns of a determinant are identical, all corresponding elements are same, then the value of the determinant is 0. So if any two rows of a determinant are identical, the value of the determinant is 0. Here the word identical means corresponding elements are same. So if two rows or columns are having the same elements, then the value of delta will be equal to 0. So to understand this, we will consider an example. So delta is equal to 3 2 3, 2 2 3 and 3 2 3. So we can expand it using the first row. So 3 into 2 3 2 3 minus 2 into 2 3 3 3 plus 3 into 2 2 3 2. On simplifying, we get 3 into 6 minus 6 minus 2 into 6 minus 9 plus 3 into 4 minus 6. So on simplifying, 6 minus 6 is 0, so 0 into 3 will be 0. Next, minus 2 into minus 3 plus 3 into minus 2. So 6 minus 6 is equal to 0. So we can see when we expand the determinant along R1, we are getting the value of delta as 0. And this can be done directly by using the property 3. By using the property 3, we can see that the first row elements and the third row elements are identical. That is, corresponding elements of first row and third row are same. So directly using the property 3, we can say the value of determinant is 0. Next, property number 4. If each element of a row of a determinant is multiplied by a constant k, then its value gets multiplied by k. So here we are using the property of scalar multiplication. That is, if we are multiplying a row or column with some number k, then each element of that row or column gets multiplied by k. So note, by this property, we can take out any common factor from any one row or any one column of a given determinant. Second, if corresponding elements of any two rows of a determinant are proportional, then its value is 0. The second note is according to the property 3 and the first note is according to the property 4. So let us understand an example. So evaluate 102, 1836, 134, 17, 3 and 6. 102, 1836, 134, 17, 3 and 6. So the first row is a multiple of 6. So we can take out 6 in each element and write it as 102 can be written as 6 into 17, 18 can be written as 6 into 3 and 36 can be written as 6 into 6. Rest of the rows we will keep it as it is. Next, on taking 6 common from the row 1, we get 6 into 17, 3, 6, 1, 3, 4, 17, 3 and 6. Now we can see that using the property 3, the elements of R1 and R3 are identical. So the value of determinant will be 0. So 6 into 0 will be equal to 0. So in this example we have made use of both property number 4 and property number 3. Next, property number 5. If some or all elements of a row or column of a determinant are expressed as sum of two terms, then the determinant can be expressed as sum of two or more determinants. So here the property means that if the elements of a row are expressed as sum of two elements, then the entire determinant can be expressed as the sum of two determinants. So to understand this, we will consider an example. So show that A, B, C, A plus 2x, B plus 2y, C plus 2z, x, y, z is equal to 0. So consider the LHS part. So you can see every element of the second row is sum of two elements. So we can split the entire determinant as sum of two determinants, that is ABC, then the first elements of the second row and the third row elements, plus ABC and the second elements of the second row, that is 2x, 2y and 2z and x, y, z. Now using the property number 3, we can see that the first row and the second row of the first determinant are identical. So the value of determinant will be 0. And in the second determinant, we can see that the values of R2 and R3 are proportional. That is, if you take out two common factors from R2, the elements of R2 and R3 will be identical. So value of the determinant using the property 3 will be 0, and 0 plus 0 we get 0, which is the required RHS. Next, property 6. If to each element of any row or column of a determinant, the equimultiples of corresponding elements of other row or column are added, then the value of the determinant remains the same. The meaning of this property is that if we apply the operation Ri implies Ri plus k Rj, then there is no change in the value of the determinant obtained. Similarly, we can make use of the operation Ci implies Ci plus kCj. So when we apply these two operations, that is either the row operation or column operation, then there is no change in the value of the determinant. So using the properties of determinants and without expanding, prove that x a, x plus a, y b, y plus b, z c and z plus c is equal to 0. So we have already discussed the 6 properties of determinant. So using these properties we need to prove the above determinant. So the determinant is x a, x plus a, y b, y plus b, z c, z plus c. So by applying the property C3 implies C3 minus C2, we get the elements of C3 will change to C3 minus C2. So write down all the elements of C3 and use the elements of C2 to take the difference of C3 and C2. On simplifying, we can see the new elements of the C3 will be x, y and z. So when we substitute these values in the determinant, we can see that the elements of C1 and C3 are identical. Therefore, by the property 3, we say the determinant value of A is equal to 0. Next, using the property of determinants and without expanding, prove that A minus B, B minus C, C minus A, B minus C, C minus A minus B, C minus A minus B, B minus C is equal to 0. So again we will consider the given determinant as A. So we will apply the property C1 implies C1 plus C2 plus C3. So the elements of C1 are getting changed to C1 plus C2 plus C3 and rest of the elements we are keeping it as it is. So add the elements of all the 3 columns. So the first element of the C1 will be A minus B plus B minus C plus C minus A. Second element will be B minus C plus C minus A plus A minus B. And the third element will be C minus A plus A minus B plus B minus C. Keep the elements of C2 and C3 as it is. Now on simplifying, we get the first element of C1 as 0, second element as 0 and the third element as 0. Now we can see that all the elements of C1 are 0. So on multiplying with 0, the entire determinant will be equal to 0. Next question, using the properties of determinant and without expanding, prove that 2 7 65, 3 8 75, 5 9 86 is equal to 0. So consider the given determinant as A. Next, we apply the property on C3. That is, we rewrite the elements of C3 as 65 can be written as 9 into 7 plus 2. 75 we are writing it as 9 into 8 plus 3. And 86 we are writing it as 9 into 9 plus 5. Now on simplifying, using the property 5, we get 2 3 5 7 8 9. 9 into 7, 9 into 8 and 9 into 9 plus 2 3 5 7 8 9 and 2 3 5. Now you can see in the first determinant the elements of C2 and C3 are proportional. So the value of the first determinant will be 0. Similarly, in the second determinant, the elements of first column and the third column are identical. So the value of the second determinant will also be 0. So 0 plus 0 is equal to 0, which is the required RHS. Next question. Without expanding, prove that delta is equal to x plus y plus z, z plus x, zxy, and 1, 1, 1 is equal to 0. So we apply the property R1 implies R1 plus R2. So when we apply this property to the given determinant, the elements of R1 will be x plus y plus z, x plus y plus z, and x plus y plus z. The elements of R2 and R3 will remain as it is. Next, we take out the common factor x, y, z from the first row. So the elements will be 1, 1, 1. Now we can see that the elements of R1 and R3 are identical. So value of the determinant is 0. So x, y, z into 0 will be equal to 0. Next, using the property of determinant and without expanding, prove that 1 BC A into B plus C, 1 CA B into C plus A, 1 AB C into A plus B is equal to 0. So we will consider the LHS of the given determinant. We will apply the property C3 implies C3 plus C2. So before applying the property, you can just expand the elements of C3. That is A into B plus C, it will be AB plus AC, B into C plus A, it will be BC plus BA, and C into A plus B, it will be CA plus CB. So we will apply the property on C3. So on applying the property on C3, we get AB plus AC plus BC, BC plus BA plus CA, CA plus CB plus AB. So you can see that the elements of C3 are same. So we can take out the common factor as AB plus BC plus CA. So on taking the common factor from the column 3, we get 1, 1, 1 BC CA AB and 1, 1, 1. So the elements of C1 and C3 are identical. So using the property 3, the value of the determinant will be 0. So AB plus BC plus CA into 0 is equal to 0. Hence the RHS. Next, using the properties of determinants and without expanding, prove that B plus C, Q plus R, Y plus Z, C plus A, R plus P, and Z plus X, A plus B, P plus Q, and X plus Y is equal to 2 times the determinant APX, BQY, CRZ. So consider the LHS. So we'll interchange the columns and rows of the determinant. So when we interchange the rows into columns, we get B plus C, C plus A plus B, Q plus R, R plus P, P plus Q, Y plus Z, Z plus X, and X plus Y. So we will apply the property C3 implies C3 minus C1 plus C2. So using this property, we get B plus C, C plus A minus 2C, Q plus R, R plus P minus 2R, X, Y plus Z, Z plus X, and minus 2Z. We can take out minus 2 common from C3. So minus 2 is common. Next we will apply the property on C1 and C2. So on C1 we will apply the property C1 implies C1 minus C3, and on C2 we will apply the property C2 minus C3. So the elements of C1 and C2 will change to minus 2 into, so see C1 minus C3, first element of C1 is B plus C and first element of C3 is C. So B plus C minus C, it will be B. Similarly, Q plus R minus R, it will be Q, and Y plus Z minus Z, it will be Y. Similarly, in the second row, you can see C plus A minus C, it will be A. R plus P minus R, it will be P, and Z plus X minus Z, it will be X. So we are getting minus 2 times BAC, QPR and YXZ. Next, on interchanging C1 into C2, the sign of the determinant will change. So minus 2 becomes plus 2 and the determinant will be A, B, C, P, Q, R, X, Y, Z. So we have obtained the RHS. Next question. Using the property of determinants and without expanding, prove that 0A minus B minus A0 minus C BC0 is equal to 0. So solution, consider the determinant 0A minus B minus A0 minus C BC and 0. So if you observe the determinant, the principal diagonal elements are 0 and rest of the elements are same in number but opposite in sign. So you can see we have both A and A, minus B and B, and minus C and C. The values are same but the signs are opposite and all the diagonal elements are 0. So such a matrix is a skew symmetric matrix of order 3, and for a skew symmetric matrix of order 3 the determinant value is 0. So directly by using the property of skew symmetric matrices we get the value as 0. Next, using the property of determinants and without expanding, prove that minus A square AB AC BA minus B square BC CA CB and minus C square is equal to 4 times A square plus A square into B square into C square. So consider the LHS. So a very simple example. So what we are doing is, first we are taking A common from R1, next B common from R2 and C common from R3. So A, B, C is common. We get minus A, B, C, A minus B and C, and A, B minus C. Now next what we are doing is, again we are taking common, that is we are taking A common from C1, B from C2 and C from C3. So we get the elements of the form minus 1, 1, 1, 1 minus 1, 1 and 1, 1 minus 1. So now we will apply the property R1 implies R1 plus R2. So when we add these two rows, we get 0, 0, 2. Next 0 minus 2, 2 and 1, 1 minus 1. So on further simplifying using R1, we get A square into B square into C square into the determinant 0 minus 2, 2, 1 minus 1 minus 0 into 0, 2, 1 minus 1 and 2 into 0 minus 2, 1 and 1. On simplifying, we get A square, B square, C square, 0 minus 0 plus 2 into plus 2. So on simplifying the bracket, we get 2 into 2, which is equal to 4. So the overall answer will be 4 times a square b square c square, which is the required RHS. Next example.